Hi everyone. Can you please confirm if everything is good? I'm audible. Okay. So let's just see if things are good and then we can start, right? Yeah, okay. So I think everything is good. So first of all, tell me how was the test? Was it too hard, too easy? And particularly about the linear algebra? So in today's discussion, we are going to solve linear algebra questions, right? So which means that the combinatorics questions we are going to solve after a while, okay, after 1 2 hours. And first we are going to see the linear algebra. So this is the first discussion where we are going to see the linear algebra session. Okay, so let's just get started. First, tell me, like how was the test? Particularly regarding the linear algebra, can you tell me what was it easy to moderate? Or was it towards the tough side? What do you feel? Okay, so it was moderate. Okay, so people are saying it was from easy to moderate. Okay, test was standard. Yeah. Okay. Thank you so much. So let's start with this question. This is the first question that we have in the test. They are saying that you consider a equation which is, let's suppose, something like this, and then they're asking that here A, B, C, this A, B, and C, these are scalars, and then they're asking which of the following is true. So let's just read out the first option. They are saying if B1, B2, B3 are linearly independent, then there is only one possible combination of ABC that satisfy the linear equation. So what do you think? If you are having something like this, if you are having B equal to AB1 plus this is, see, this B and this B is different. This is a bold B, which is a vector. Okay, so maybe if you are confused, I can represent like this. So B2 plus CV3. Okay, so if you are having something like this, and then they are saying that one of the solution is given like this, and where ABC are scalars, I mean these are not known to you, then if B1, V2, V3, so there are two cases. If these B1, V2, V3 are linearly dependent, or they could be linearly independent. If they are linearly independent, let's suppose, then in this case, what do you call? What do we say? In this case, we will say that there is only one possible solution, right? There is only one possible solution. And why that is the case? See here. See, in this particular video, which is the video number 4E, we have talked about one amazing fact about linear combination of linearly independent vectors. So the video title is this, that linear combination of linearly independent vectors is unique. Have you watched this video? If you watched this video, then this question must have been very, very easy. Okay, so if you watch this video, so in this video itself we have talked about that if you are having any linear combination, and in this case if b1 b2 b3 are linearly independent, then there is exactly one solution, right? There is exactly one solution. So which means here we will say that there is only one possible combination of ABC that satisfies this equation, right? So that's why this A is correct, right? That's why this is correct. So somebody is asking, sir, I'm watching your recorded lecture of EM. Will this be complete for GATE? Yes, obviously, like, I mean, if you are watching EM from Go classes, then I mean, any subject from Go classes, it should be very much exhaustive, right? It should be complete. So don't worry about it. So that's why A is the true option. And since A is true, that's why B is false. Because B is saying if B1, B2, B3 are linearly independent, then there is only one possible combination. See, if they're linearly dependent, then there are infinitely many solutions, infinitely many combinations. That's what we talked about in this particular video. I'm not going to explain the whole concept because it will take 10 to 15 minutes just to solve one question. So that's why I will just ask you to refer this 4E, okay? 4E, where we talked about one amazing fact, okay? Just refer this 4E, lecture number 4E. This B is wrong. There is always one possible, there is always one unique combination of ABC regardless of whether B1, no, that's not true. I mean, this is false. Now, let's talk about D. Yeah, D is little controversial. Let me talk about it. They are saying if B is same as one of the vectors, which means they are saying if B is same as maybe one of the vectors B1, or maybe B is same as B2, or maybe B is same as V3, then there is always one possible combination of ABC that satisfy the linear equation. So looking at this option, this is correct. I mean, actually, I will update the answer key, don't worry. So D is also correct. I actually wanted to ask, there is always one unique possible, there is always one unique combination. Instead of possible, I wanted to write unique. Okay, but that's fine. I mean, I wanted to write unique, but that is okay. I mean, the question actually I wanted to ask is basically about the unique. Instead of possible, I wanted to write unique, but that is okay. In case if I'm writing unique, then in this case this D is false. Okay, see, currently let's talk about the two possibilities. Currently, if I'm saying possible only, okay, then just read out this D option. Is this true or false? If B is one of the vector, then obviously you have one possible solution. Then there is always one possible combination, right? So there is always one possible combination, which means, let's suppose if B is, let's suppose V1, then you can represent V equal to 1 into V1 plus 0 into V2 plus 0 into V3. So that's why this one possible combination is there, right? So here A equal to 1, B equal to 0 and C equal to 0. So this is one possible combination. One possible combination. And they are talking about the same thing. That is why I will say that D is also correct. D is also correct. Don't worry. Okay. We will make it correct. We will just re-evaluate it. Okay. D is also correct. But let's suppose that my intention was not actually to write this possible. Let's suppose that here, if I'm writing unique, okay. So instead of possible, let's suppose here I'm writing unique. Okay. Suppose instead of possible, I'm writing unique. Then what will the answer? Will this be true or false? If I'm saying unique. So now the question becomes this, that if B is same as one of the possible vector, if B is same as B1 or B is same as B2 or B is same as B3, then there is always one unique combination. Will this be true? I don't think so, right? So yes, let's suppose B is same as B1. Then yes, that is one combination. But there could be some other combination also, right? Suppose V2 and V3 both are equal. I mean, you don't know about V2, V3. Then let's suppose this is also the one possible combination, right? If B2 and V3 are equal. I mean, you don't know about V2 and V3. I mean, there could be linearly dependent. That's what I mean, right? There could be linearly dependent. So in this case, this will be false, right? So in this case, actually I wanted to write unique, but somehow I have written possible. But anyway, that's okay. In this case, this statement is false. Okay, but coming to the question, this current statement, this because of this possible, the current statement is true. Okay, so that's why the answers are I have updated the answer key. I think it is A, D. Okay, answers are A, D. Is this okay to everyone? Okay. Now let's look at the second question. So now in the second question, what they're asking, let's just talk about it. So they are saying that let A be the matrix and B be the column vector, given that Ax equal to B has at least one solution, and they have given the solution also. So they are saying that Ax equal to B is having one solution, okay, which is 1, 2, 3. Let me call this vector as U. So maybe I can say AU equal to B, right, where U is 1, 2, 3. Is this okay to everyone? I mean, I'm saying that Ax equal to B has one solution, which is, let's suppose U, and I'm calling it I'm calling it U, which is 1, 2, 3. Now again they are saying that Ax equal to 0 is also having one solution, which is 4, 5, 6. So let's suppose that Ax equal to 0 is having one solution. Let me call this vector something, let's suppose n. So I'm saying An equal to 0 is also satisfied, where n equal to 4, 5, 6. Okay, so I have two relation here, which are as follows, and then they're asking what are the other solutions of Ax equal to B. So I have these two equations, right? Now using these two equations, can you give me the other solutions of Ax equal to B? What could be the other solutions? Here, if you add these two equations, then what you will be getting? You will be getting U plus n equal to B. So you can say if U is a solution of Ax equal to B, and n is a solution of Ax equal to 0, Using these two facts, fact number 1, fact number 2, using these two facts, what can you say? You can definitely say that u plus n is a solution. You can say u plus n is a solution of ax equal to b. U plus n is a solution of ax equal to b, right? Is this okay to everyone? Let me know. Is this okay? U plus n is a solution of ax equal to b. So I hope that is fine. Now, is this just u plus n? Or you can also multiply some multiple k here, and then you can add. Before adding, can't you just multiply some multiple k? So basically, if I'm having, see, if I'm having au equal to b, if I'm having an equal to 0, this is equation number 1, this is equation number 2, which are given to me, right? This is given to me. Now, can I not do multiple, can I not multiply here k, which means can I not say that kn equal to also 0, right? I mean, that is also fine. Let's suppose this is equation number 3. Then add 1 and 3. Then what you will be getting? If you are adding 1 and 3, what you will be getting? Just tell me. If you are adding 1 and 3, then you will be getting you can take a common, u plus kn is also b, isn't it? So from here, can't you say that u plus kn is also the solution, right, of ax equal to b? Yeah, k could be positive or negative. It could be anything, right? So adding or subtraction, both are possible. Okay. So it could be positive or negative. So add, subtract, it is up to you. So which means that you are saying that you take the solution of ax equal to b, and then you multiply any solution of ax equal to 0 with k, and then you add it. Then it is a solution of ax equal to b. So here you can say you take the solution of ax equal to b, which is 1, 2, 3. You take k and then you multiply 4, 5, 6, right? Then this is a solution of, this complete thing is a solution of ax equal to b. Solution of ax equal to b, right? This complete thing. So that is why you will say that I think what are the options that are satisfying? If you do 1, 2, 3, and I think you take k equal to -1 probably, then this option B will satisfy, right? If you take k equal to -1, option B will satisfy. If you take k equal to 2, then I think option D will satisfy. So what are the answers? What are the answers? B and D. B and D. Okay. Okay. They must be also the solution of ax equal to b. Right? From this information, you can only derive this. Okay. You are getting V when k equal to -1. You are getting D when k equal to 2. Okay. Great. Now let's just move further. Okay. So let's talk about this question. What they are saying, let A and U be this, then compute A power 2023 into U. Were you able to solve this question? What was the answer? What was the answer here? See here, if you just multiply A and U, then you can easily observe you are just taking first column, I mean 1 into this and 0 into this, which means it will be A into U if you just multiply using the shortcut that we have discussed. This is -1 and 0, right? Now, if you do one more time, if you multiply again A, I mean if you multiply again A to this, then what will the answer? So if you multiply A to AU, right? Which means multiply A to -1 and 0. So you will be getting 1 and 0, right? You will be getting 1 and 0 in this case. So which means that AU is -1 and 0, and A square, this is nothing but A square U, right? A square U is 1 and 0. Now if you do one more time, what will be the answer? If you multiply, if you multiply one more time, see, this is just U, right? A square U is just U. It is just U. I mean, there is no difference between u and a square u. So basically, if you are multiplying a and u, it is giving you minus u. If you are multiplying a square u, it is giving u, right? So basically you can say au is giving you u, a square u is giving you minus u, isn't it? So that's what we have observed. Now you do it multiple times. So basically you can say, if you do it multiple times, a cube u will again be u, because if you do if you multiply a here, it will be a cube u, or au is already u, right? So a cube u will be u. How? You can basically easily check it. I mean, I think it is very intuitive, but anyway, you multiply a here, so this will be a cube u, you multiply a here, that is au. Okay, just a second, it is yeah, a cube u is should be u or minus u. See, au, okay, au is minus u, sorry, au is minus u, a square u is plus u, then it will be minus u only, right? Yeah, so a cube u is minus u. Why? Because if you multiply this with a, then you will be getting again minus u. So basically, a to the odd power you are getting minus u, and if it is even power, then you are getting plus u, right? If it is odd power, then you are getting minus u. So which means a power 2023 u is minus u, which means B is the correct answer here. Sorry, A is the correct answer here, minus u, right? A is the correct answer here. Is this okay to everyone? So you can quickly observe it that AU is basically giving you the minus of this vector, which means if let's suppose in this question, if they ask you that that if the eigenvector of, if in the same question, if they ask you eigenvector of A 2023 will be what, and eigenvalue of will be what. Since you know that A 2023 u is giving you minus u, right? Minus u. Then you will say the eigenvector will be u and eigenvalue will be minus 1. Okay. They could have asked this question also. Eigenvector and eigenvalue. They could have asked this question also. Okay. So you can consider it just like a variation. I mean, in the same question, they could have asked this kind of thing also. Okay. So I hope you understood now. Now let's see this. Yeah, that's very interesting question. But before this, let me just ask you, have you seen this particular lecture? The lecture number 10D? This thumbnail is saying IIT professor's favorite question. Okay, IIT professor's favorite question. So that has been asked in GATE 2-3 times in 2018-22 and asked many times in interviews. And this is basically the relationship between the eigenvalues of AB and BA. Have you seen this particular lecture? Lecture 10D. So the lecture 10D talks about the relationship between the eigenvalues of AB and BA, a concept asked many times in interviews and also in the GATE, as you can see. And it is a very nice concept. Let me quickly just tell you one concept, which is saying that non-zero eigenvalues of AB and BA are same. Okay, non-zero eigenvalues of AB and B are same, which means let's suppose AB is having 3, 4, 5. These are the eigenvalues that AB is having. Then BA must be having 3, 4, 5 eigenvalues. Okay. If this is 0, then it doesn't matter. I mean, 0 it need not to copy, but non-zero it will definitely copy. Have you seen that lecture? I have talked about the proof also, that eigenvalues of AB and B are same. I mean the non-zero at least. Okay. So now let's just see this question, what they are saying. If you want, I can quickly prove it, but the solution or the proof is already there in this particular video, and you should be able to find the proof. And that's a very nice proof. You can just watch that particular video. That's a very important video also, because with respect to GATE and with respect to IIT professors interviews, this particular question has been asked many times. Now let's just solve this. Now what they are saying is this. Let me just try solving it. See, they are saying that consider two column vectors u and v belonging to the vector space R5. If the dot product between these vectors is 10, which means what will the matrix UV transpose, where UV transpose is dot product means what? Dot product must mean that you can, this U is basically, they are saying u and v are 5 cross 1 vectors, right? 5 cross 1 vectors. So dot product means like you can take it 1 cross 1, u transpose into v, right? Into v. So this will be the dot product. So if you see the dimension here, it will be 1 into 5, and this will be 5 into 1, and ultimately it will be just 1 into 1. This is just a scalar or 1 into 1 matrix, whatever you want to treat it, right? A scalar. So this is the dot product. But if you talk about this UV transpose instead of U transpose V, see, if U is 5 cross 1, V is also 5 cross 1, then UV transpose will be, this will be 5 cross 1, this is 1 cross 5, this is a matrix of 5 cross 5, right? A matrix of 5 cross 5. But if you talk about U transpose V, then this is 1 cross 5, this is again 5 cross 1, right? And then it will be 1 cross 1. So you can say it is a matrix of 1 cross 1 or the scalar, right? Of 1 cross 1. I mean, it will depend how you are treating it. Scalar doesn't matter, basically. Is this okay to everyone? Okay. So UV transpose sometimes called outer product also. Okay. Anyway, so now let's talk about the question. So they are saying that the dot product is 10. They are saying that this quantity is just 10. The dot product is 10. So what does this mean? If you treat it as just like a matrix of 1 cross 1, can you tell me the eigenvalue of this? Eigenvalue of this matrix? Eigenvalue of this is just 10, right? If you treat it just a 1 cross 1 matrix, then eigenvalue of this is just 10. Is this okay to everyone? Now, if as I just told you that AB and BA shares same eigenvalue, share same eigenvalues. At least they share, non-zero is there. They share the non-zero eigenvalues should be same. Okay. So let's just talk about it. So they are saying UV transpose, right? So see, now if you talk about UV transpose, similarly, this is what a given matrix of 5 cross 5. Okay. And V transpose U, which is if you take the dimension of it, it will be 1 cross 5 and 5 cross 1, basically, right? Which is 1 cross 1, right? And which is a matrix of 1 cross 1 matrix. These two matrices, this matrix and this matrix, these two matrices should also share same eigenvalues. Isn't it? Which means what? If this is given to be 10, so basically the eigenvalue of this matrix is just 10. So this must be having 10 as one of the eigenvalue, and the this is the only non-zero eigenvalue. Okay, because the non-zero eigenvalues are same, and since it is 5 cross 5, it must be having some other eigenvalues. And what must be the other eigenvalues? These must be the 4 zeros, because the non-zero must be same. Actually, I talked about this in the lecture, so that's why I'm directly solving this question. But I talked about this in this lecture very much exhaustive. Okay, just watch this lecture. So basically, this must be having 10, 0, 0, 0, 0, 4 times 0 and 10. This must be the eigenvalues of this. And then they're asking trace of this. Trace means sum of all the eigenvalues, which means 10 only. Right? So have you understood what I'm saying? See, this UV transpose and V transpose U, the eigenvalues must be same, right? So non-zero at least, non-zero eigenvalues must be same as non-zero eigenvalues here. Zeros doesn't matter. Actually, I talked about this concept very nicely here in the YouTube video. If you want, you can watch this video. Okay. So it is given that this is having 10 as non-zero, so it must be having 10 as non-zero. And since it is 5 cross 5, that's why there must be 4 other eigenvalues. So can you tell me what are the 4? This cannot be non-zero. Non-zero must be same. That's why this cannot be non-zero. That's why these must be zeros. Okay. Again, just watch this video, please. Okay, because otherwise it will take half an hour to explain just one question. That's why I'm again and again saying watch that video. So the eigenvalues of this are this. So that's why trace of UV transpose is just 10. Okay. Is this okay to everyone? So someone is asking, sir, can we say that if a matrix with dimension n cross 1 is multiplied with another matrix, we will be having only one non-zero eigenvalue? Yes, that is correct. So that's a nice observation. So someone is saying that a vector, let's suppose a vector which is n cross 1, okay, n rows and 1 column, which means this. If we are multiplying this vector, which is having this vector with this vector, which is 1 cross n, okay, and this is n cross 1. So basically, finally you will be having n cross n matrix, right? Now, someone is saying that this matrix must have only one non-zero eigenvalue. That is correct. Okay, this matrix must have only one non-zero. Okay, and why that is the case, you please refer this. Okay, please refer this. Cool. Now let's talk about this. Have you solved this question? So if you watch this particular video, which is one of the most important video in our whole linear algebra playlist, which is a new approach to apply multiply and a vector. Okay, new approach to multiply a matrix and a vector. If you watch this particular lecture, then which is the most important lecture in the whole series. Okay, so basically, if you have watched this particular lecture, then you could have solved it. So basically, they are saying that there is some matrix M which is given something like this. The rows and columns and even the diagonal sum up to 12. That's what they are saying. Then they are saying find the value of this. See, if you are having some matrix M and then you are multiplying it with 1 1 1 2 2 2 3 3 3, then obviously what you will be doing, you will be basically adding all the columns to 1. This is what it is saying, right? So you will be the way to multiply, just please refer this particular lecture again. Okay, this is the most important lecture in the whole series. Just please refer this lecture, then only you will be able to understand. Okay, so see, they are saying that if you multiply this, then this 1 1 1 indicates that you are going to add all of these vectors, and then you are going to have first vector here. So as they said, like if you are adding all of the columns, then it should be 12 12 12, right? And then you are adding with the multiple of 2. It is 24 24 24. This is 36 36 36. So that's why, what is the answer here? Okay, so gravity is one user who is saying that I created one of the magic matrix unnecessarily and solve this question. You don't need to do it. Okay, the answer is very much straightforward, which is B. How many of you did it directly without creating the matrix and all? How many of you you did it directly? It is a direct question, right? Okay, so I hope you understood this. So just watch this lecture if you have not understood this. This is the most important lecture in the whole series, I will say. Okay, just watch this lecture if there is any confusion. Now let's see this. Consider a matrix A that is 3 by 3 and which is as follows. It is observed that last column of the matrix A is obtained by adding twice the first column of the second column. Twice the first column to the second column. So basically they are saying that this column, you can easily observe, this column is 2 into 1, 2, 3 plus 3, 6, 7. And then you will be getting 5, 10, 13. So that's what they are saying. I mean, if you do the twice of this and plus this, then you are getting the third column. I mean, this is just one observation that you can make. Now, after performing some unknown elementary row operations on a matrix A, we get the matrix R as shown as this. Okay. Now they are asking the value of A plus B plus C. Now they are asking the values of A plus B plus C. So see, this is quite an easy question. Why that is easy question? Because there is one very important observation if you want to make, that if you do the elementary row operations, irrespective of what operation you are doing, if you are doing elementary row operations, then in that case, the relationship between column doesn't change. Okay, that's very much important. Okay, after elementary row operations, relationship between yes Saurabh, doesn't change, which means if earlier this is the relationship, then also this is the relationship, which means this ABC, you can say this ABC. Okay, whatever is the earlier relationship, the same relationship will hold here also, which means you can say this ABC can also be treated as 2 into the first column, 1 0 0 plus 1 into the second column, which is 0 1 0. Okay, 0 1 0. Now if you solve this, A will be 2, B will be 1, C will be 0, right? The relationship between the columns doesn't change. Yes, so that's why A plus B plus C is 3. That's why this is 3. Okay, so that's how you can solve this question. Anyway, I talked about this particular concept in this particular video. Okay, so you can watch this video, lecture number 6E. This is the lecture number 6E. Okay, you can watch this video 6E, and here I particularly talked about this particular concept. Okay, so the relationship between, I mean, you don't need to do all of the elementary row transformation to get this matrix. How many of you did it? How many of you did using the long method? And how many of you did using the short method? See, one other method could be, you take this matrix A and check what are the operations that are leading to R, right? And then find the values of ABC. This is the long method. I can say this is the long method, which is not required. How many of you did using the short method? So yes, some of you have done it, right? So some of you, or I can say many of you. That's very good. Cool. Now let's go to the next question, which is this one. Yeah. Have you watched one of my lecture of LU decomposition, which is the lecture number 11A? Have you watched this lecture number 11A of the of LU decomposition, where we have talked about a shortcut to find out the decomposition? Okay, so if you watch this lecture, then I think this should be straightforward, right? So this is straightforward. After watching LU decomposition. Okay. So this is one question which I've taken from one university. I think the solution is there on the website. So whatever you're doing, see in the L, see they are saying subtract. So this is 1 0 0, and then this is 0 1. Sorry, this is 1 0. This is 1, right? So basically you need to fill 1, 2, 3 entries. These are the 3 entries that you need to fill. So 1 entry that you need to fill, 2 and 3. Now Yes, options C and D are same here. I mean, by mistake, I put it same. So I will mark both the options to be correct. Okay. So I will mark both the options to be correct. Don't worry. Okay. So C is also correct. D is also correct. We will give marks to both of them. C and D. C or D. Okay. If you mark C or D, both are correct. So see, they are saying subtract 3 from first row, subtract 3 times the first row from the second row. So basically for subtracting, then it is -3, but it is opposite of sign, which is +3. You will be writing +3 here in the L, right? Have you watched this lecture? If you watch this lecture, then it should be clear. Okay. If you watch this lecture, then it should be clear. Okay. Now, let's talk about it. I think this is one easy question. What they're saying, if A and B are n cross n matrix, then trace of this, trace of AB and trace of AB is equal to trace of A into trace of B. I think that's wrong, right? You can probably easily construct the counter example that trace of A into trace of B. Okay. So, maybe I have one counter example here. Yeah. So here, as you can see that this is A, this is B, right? Now, if you talk about AB, which is 0. So trace of AB is 0 basically. I mean, trace of AB is 0, but if you individually do the trace, then it is coming out to be 1. Okay. So this is the counter example that you can see. Okay. So I hope you can see this. So basically that is why this is wrong, and trace of A plus B is same as trace of A plus trace of B. That is quite intuitive also, because trace is just the summation of diagonal elements. If you're summing it up first and then you're summing it, I mean summing the diagonal elements of A, summing the diagonal elements of B, and then, or you are first adding them and then you're summing it. So both should be fine. I hope you understood. See, so what I'm saying here is that this is A, this is B. If you want to add both the matrices, then anyway this element will get added to this element. So basically diagonal elements will anyway be added, right? So first you add, then I mean it is basically just a trace of A plus B is nothing but summation of all of these numbers, right? All of these numbers. So it is, let's suppose these numbers are A, B, C, D, E, F. Then this is A plus B plus C plus D plus E plus F, right? Either you first find A plus B plus C first, and then D plus E plus F, and then you do the addition, or you can just first add both the matrices and then you can find the trace. So basically it should be same. Okay, that's great, Ankit. So Ankit is saying that he is enjoying the lectures and he has come to the 6E. That's really nice. Okay, someone is saying that one interesting thing that I saw was many from the top 20 got 40 plus in under 20 minutes, less than 1 minute per question. Yeah, don't worry, we will check it. I mean, don't worry, we will disallow all of these submissions. So our scholarship is very worthy. We can't just we can't just give it anyway. Okay, so we won't be giving the scholarship like that. Okay, our scholarship is actually, it's not like, I mean, it's not only about the money, it's about the worth. So our scholarship is worthy. We won't give it like that. Okay, don't worry. To cheaters, don't worry, we will make some arrangement. Okay, now let's just see this. They are saying let A be the matrix of 4 into 3, and then the system AX equal to B has a unique solution for some B. What does this mean? Unique solution for some B, it means what can you immediately say? That columns of A are linearly independent, right? Columns of A are linearly independent, and no solution for some other B. It means what? They are not filling the space, and obviously they cannot fill the space because this is 4 rows and 3 columns, right? So basically these are just three vectors in R4. So obviously, I mean, this information is actually redundant, I can say. No solution for some other b. This is redundant. They do not need to give it. Okay, redundant. That's what you already know, right? I mean, you already know this. They do not need to give this information. We know this, right? Then the possible rank of A. See, they are saying that you are having 3 vectors and all the vectors are linearly independent. Then what are the rank? What is the possible rank? The only possible rank is 3, right? The only possible rank is 3. Okay, so there should not be any confusion here. Now let's just see this. That's one interesting question. You don't need to, here this AB inverse is given, which is basically, you can say this is B inverse into A inverse, which is given to be -3, 2, 1, -1, right? And then A transpose is given, which means A is also given to be, you can just take the transpose of it, which is 1, 0, right? A is given to be this, and AB inverse is given. They are asking for the B inverse. So maybe, yeah, so what you can do, you can basically just try to find the B inverse by multiplying the A here. So B inverse is nothing but A into this particular matrix, which is -3, 2, 1, -1, right? I think that is the way. So A is what? A is this. So you can basically, you can find out B inverse, A inverse is given to be whatever it is, right? -3, 2, -3, 2, 1, -1. And A is given to be 2, 1, 3, 0. A is given to be 2, 1, 3, 0. Now you can find out B inverse as, you multiply A here, maybe the post multiplication you need to do, right? So which means -3, 2, 1, -1 multiplied by 2, 1, 3, 0. I think this should give you the answer. Yeah, post multiplication. Yeah, sorry, here it is post multiplication. Yeah, that's correct. So you need to multiply A here. Okay, so that's how you can find out B inverse. I think that is fine. Now let's just see this. I think this question was also straightforward. They are saying that given this matrix and there are some unknown columns which are given to you. This AB is having some unknown columns, but one thing is for sure that the second column is 1, 2, right? Now in this scenario, the second column of B is known while the other columns are unknown. Find out the second column of matrix B. So what is this A here? A is also given to you, right? A is given to you. It is 2, 0, 1, 1. And what you need to multiply? What you need to multiply here such that you get this? Can you tell me? What you need to multiply such that you get this? So basically this column, as you know, I mean every column here, like, I mean you will be doing what? You will be basically, this is 2 into 3, okay? 2 rows and 3 columns, okay? So what you will be doing? You will be taking coefficients from here and adding the linear combination of this should get you this. And similarly, if you want to get this, then you will say, let's suppose this is A and B. That's what being asked, right? This is being asked. So you can say A into this 2, 0 plus B into 1, 1 should be 1, 2. Okay, should be 1, 2. Is this okay to everyone? Now, if you see this, that we have already talked about this in our lectures. And what is that lecture? The same lecture which I talked, see here. This is the most important lecture in the whole series. If you know that how to multiply a matrix and a vector, then you can also solve that particular question. Okay, if you know how to multiply a matrix and a vector, then you can solve that particular question. So that's how we are going to solve this particular question, right? See, this is the lecture you can watch if you are not understanding this particular solution, because I cannot tell in this particular short video, I cannot tell the whole method. Okay, it will unnecessarily take time. Just go and watch this particular lecture. Okay. Cool. So that's how you can find out 2A plus B equal to 1 and then B equal to 2. So if B is equal to 2, you will be putting this B here, and then from this you will be finding out that it is A equal to -1 by 2, right? A is -1 by 2. Yes, Anirudh. That is a complete course. I mean, there is no complete or incomplete. That the engineering mathematics is, and any course which we are providing, which is engineering mathematics and discrete mathematics, that is complete only. So that's how A is the correct answer. Okay. Now let's see this. So this is very interesting. They have given you the characteristics equation and then they're asking about the trace. I think trace we can find out, determinant we can find out, eigenvalues we can find out. The only thing, can we find out the exact rank, not upper or lower bound on the rank? Can we find out the exact rank of matrix A? That's the only interesting thing, right? See here. Have you seen this particular lecture? Given the characteristic equation, what will the rank? That is the lecture 10B. Have you seen that particular lecture? If we have seen that particular lecture, that given this characteristic equation, can we find the rank? Then I think this question is straightforward after it, right? Given this characteristic equation, can we find the rank? So basically here this lambda equal to 0 is important. Since this lambda equal to 0 is there, and how many times it is repeating? Just one time it is repeating, right? One time. Repeating means that power of this is 1, right? Power of this is 1. So see, if you watch this particular lecture, then it will be very much straightforward, but still I'm just telling you that it means that there is one linearly independent eigenvector corresponding to lambda. Eigenvector corresponding to 0. Right? And hence since there is just one eigenvector corresponding to 0, so because it is just repeating one time. If it is repeating 2 times, then we don't know actually, and you can see that particular lecture here. Okay, if let's suppose if it is repeating 2 times or maybe 3 times as per in this thumbnail. Okay, let's suppose if it is repeating 3 times, then in that case number of linearly independent eigenvectors for lambda equal to 0, you don't know basically, right? I mean, it will be less than equal to 3. Okay, it will be less than equal to 3. But here it is exactly equal to 1. It is exactly equal to 1, and that is what nullity is. That is what nullity is. And since it is nullity, so nullity is 1, and that is why rank will be, you can find out the rank. And what will the rank? Here the degree of this polynomial is 2 plus 1, 3 and 4, right? So rank will be n minus nullity. So this is 4 minus 1, which is 3. So you can say you can find out the exact rank. So yes, you can find out the exact rank, right? So that's how you can solve this particular question. You can definitely find out the exact rank. And if you are a little bit confused, then I suggest you to watch this lecture number 10B. Okay, just watch this lecture 10B here in the playlist that we already shared with you. Okay, great. Now let's talk about this question number 13. Okay, let's talk about this question number 13. So what they're saying, that A is a matrix where the trace of A square is 5, which means, do you know the if eigenvalues of A are lambda 1 and lambda 2, then eigenvalues of A square are lambda 1 square and lambda 2 square, isn't it? So trace of A square, which means lambda 1 square and lambda 2 square is given to you is 5, and lambda 1 plus lambda 2 is given to you is 3. So from this you need to find out the determinant. Basically you need to find out lambda 1 into lambda 2. So you can solve this quadratic equation. I mean, this is the 2 unknowns and 2 equation. Maybe you can solve it, right? And now they are asking you to calculate lambda 1 into lambda 2. I think you can do it. Or maybe by observation only, you can you tell me? Lambda 1 is equal to maybe 2 or 1, and I mean one of the lambda is 2 and one of the lambda is 1, because summation is 3 and it is 5, or if you want you can write like this, right? Is this okay to everyone? Okay, I hope you understood. So basically it is very easy. Lambda 1 into lambda 2 is 2. I think the I mean the questions in the paper or in the exam was not tough, right? Okay. So here the answer is 2. Now let's talk about it. This is one of the interesting question that we have. Let's just talk about it. Now this is question number 14. What they are saying, if A is 3 cross 3 matrix such that A into some vector is giving you some vector, I mean this vector can be obtained using the two solutions, right? I mean the same vector you can obtain using the two solutions. The same vector. So what does this mean? It definitely mean that this vector can be having, I mean is having multiple solutions, which means it definitely mean that Ax equal to B are having infinite solutions for some B. What does this mean? If there are infinite solutions, then there must be free variable. I mean, in whatever sense you want to talk about, you can say that columns of A are linearly dependent. Columns of A are linearly dependent. Directly you can say there must be, or you can say there must be free variable. Right? Which means columns of A are linearly dependent. That's why A inverse does not, A does not have the inverse. That's true. That's true. Right? A does not have the inverse. That's very much true. Okay. Yeah, we talked about it. I mean, there is one lecture. I don't remember the lecture number. We talked about that eigenvalues of powers of A. The lecture number I don't remember, but I remember the title. Eigenvalues of powers of A. We already talked about it. Okay. I mean, if A is having the eigenvalues, if let it be lambda 1, lambda 2, then A square is having lambda 1 square, lambda 2 square. We talked about it already. Okay. There is one lecture. Okay, let's just see this particular option B. Now they are saying A is M cross N matrix of rank R. Okay, so let me just go to the next page. They are saying this is B. They are saying A is M cross N matrix of rank R. Suppose there exists right hand side B for which Ax equal to B has no solution. See, they are saying that there is some B for which Ax equal to B has no solution. So there is no solution for some B. What does this mean? If there is no solution for some B, it means that the columns are not filling the space. The columns are not filling the space. Is this okay to everyone? Okay. Now, then they are saying A transpose Y. So basically, now here, just let me know if columns are not filling the space. So what does this mean? See here. You will be having, let's suppose these are the M columns and M rows and N columns. So M rows, which means all the columns are in R power M. R power M. And the rank is R, right? So tell me, can the rank be M? Can the rank be M? Which means rank is M means there is a pivot. There is a pivot in every row. And what does this mean? If there is a pivot in every row, then there is always a solution for all V's. There is a solution for all B. Right? See, if you are having a matrix, let's suppose this is the augmented matrix, you write your B here. If there is a pivot in every row, if you are having a pivot in every row, then can't you solve for any B? Can't you solve for any B? If there is a pivot in any row, then if pivot in every row, then we can solve for any b. Right? Is this okay to everyone? I hope that is fine, right? I mean, irrespective of the b, if there is a pivot in every row, then we can solve. Or there is some confusion here. I think yes, right? So we can definitely solve. So since we are not able to solve, it means there may be, if the solution does not exist, then there may be zero non-zero somewhere, right? There may be zero non-zero somewhere. Do you remember the lectures? There may be zero non-zero somewhere, which means if you are not able to solve for some b, then there must be zero or non-zero situation. This is zero and this is non-zero. That's the only reason you are not able to solve for some b, right? So that is the case where we are not able to solve for some b. Which means what? That there is a row at least which is not having pivot. Which means that if this is 0, it means rows are linearly dependent. Can you say? From this conclusion, if you are not able to solve for some b, then it must mean that rows are linearly dependent. Right? Rows are linearly dependent. Can the columns be linearly dependent or independent? That we don't know. I mean, maybe the columns are linearly still. Can you say the columns are linearly independent? It depends on number of columns, right? I mean, how many number of columns and all. But from here, we can say that rows are linearly dependent for sure. Because if we are not able to solve, then zero non-zero must exist. This zero and non-zero must exist, which means that rows are linearly dependent. So I can say rows of A are linearly dependent. Which means columns of A transpose are linearly dependent. I mean, here it is rows, but in case of A transpose, it will be column, right? This is A, and in case of A transpose, it will be column. This is A, but in case of A transpose, it will be column. Now, I made a conclusion that columns of A transpose are linearly dependent. From what? It was given that we don't have solution for some b. This was given to me. From here we concluded that columns of A transpose are linearly dependent. Right? Okay. So let's just see this. What they're saying, that then A transpose y equal to 0 has solution other than y equal to 0. Yes. So in this case, if there is just one solution, there will be, since the columns are linearly dependent, there will be infinitely many solutions. Columns of A transpose are linearly dependent. Right? It was a nice question, I think. Sorry. Okay. So basically you will say this is also true. How? Because columns of A transpose are linearly dependent. Let's talk about this option C. Okay. See here, if the vectors a1, a2, a3 are in R4 are linearly independent, then the matrix is invertible. I think this is straightforward, right? So this C is true. This is also true. This is straightforward, that if the vectors are the columns are linearly independent, then this is invertible. If A is 3 cross 3 matrix such that Ax equal to 0 has only trivial solution, then what does this mean? It is a square matrix and having only trivial solution. It means what? That the columns are linearly linearly independent, right? Because it is having only trivial solution. Then the equation Ax equal to B is consistent. Columns are linearly independent, and you have 3 columns. I mean, it is 3 cross 3, right? You have 3 columns in R3. Then it is consistent for every B. Yes, that is also true. Okay, so that's very nice question. I can say this question number 14 was one of the very nice question. Were you able to do this? This was one of the nice question, right? Okay. Let's talk about this question number 15. This question number 15. But before this question number 15, I want to ask you, have you solved this this particular question, GATE 2021 question? That is there in this video, lecture 5E. In lecture 5E, have you solved this GATE 2021 question? That is writing down infinite solutions of Ax equal to B, right? Writing down infinite solutions of Ax equal to B. Okay. So basically this question, GATE 2021 question, and the question that we have asked here are almost same. I mean, I won't even say that there is a slight difference. I mean, the slight difference is just because that we have the 2 vectors here and they have just 1 vector here. Otherwise, this question that we have asked is same as GATE 2021 question. Right? This question is same as GATE 2021 question. So now, if I just ask you what is the answer here, then can you tell me the answer? See, you are having 2 free variables. What does this mean? Oh, sorry, you are having this parametric form. It means that you are having 2 free variables, right? 2 free variables. You can even tell the free variables, which is x3 and x4, right? x3, x4. So you are having 2 free variables, which are x3 and x4. If you are having 2 free variables, it means that the pivot variables will be, I mean, if it is 5 rows and 4 columns, 1, 2, 3, 4. If these are the free, then these are the pivot, right? These are the pivot, which means rank is just 2. Rank is just 2. That was very easy question if you have solved this particular GATE 2021 question from this video. And you have to watch this video. I mean, if you are very new, you have to watch this video. You can't just solve directly. Okay. So that was very easy question. And I put it 2 marks. The only reason is because that if you have not already solved this GATE 2021 question, then you might have to spend 2 to 3 minutes here in this question. So that's why I put it 2 marks. Okay. I think the questions were smooth. Like there was not much problem in the questions as far as I feel. What do you think? Was the questions too hard to solve? No, right? Okay, let's talk about this question. They're saying that A and B are given. I mean, system of linear equation is given, and then they're asking that which is true. I mean, this is again a MSQ, multiple select question. So what we can do, we can just have the linear transformation, elementary row transformation of this augmented matrix, and you will be getting this, right? Now, I'm not doing the row transformation. Suppose you have done it, and now we can solve, assuming that we have this row transformation with us, right? Now, if this is the row transformation that is with us, now if they ask you to solve this, then let's just solve this. Which of the following is true about the solutions of system of linear equations? The system has no solution if k is not equal to 9. Yeah, that is true. If k is not equal to 9, then it will be 0 non-zero situation, right? 0 non-zero situation. Then it will be no solution. So, yeah, that is true. Okay. Okay. So, the second is saying the system has exactly one solution if k is equal to 9. If k is equal to 9, which means it will be 0, and h is not equal to -4, which means it is non-zero. It is non-zero. So which means then it will be exactly one solution. Yeah, I think it will be exactly one solution. Even you can solve it. Maybe x2 will be something 0 and x1 will be I think 3, right? This is the exactly one solution that you will be getting. And x3 and yeah, so x1, x2, these are the only 2 variables, sorry. So these are the only 2 variables, x1, x2. So x1 will be 3 and x2 will be 0. So exactly one solution. There are infinitely many solutions if k equal to 9. I mean, that has to be 0. And h is -4. Yeah, in that case, x2 will be k. In that case, x2 will be k, right? So that's why there are, I mean, this will be the free column. This will be the free column. That's why there are infinitely many solutions. Yeah, that is also true, right? And then let's just see let's just see the option number D. The system has no solution if k equal to 9, if k equal to 9 and h equal to 4. No, it has the solution, right? In that case, again, this is the solution. Exactly one solution, in fact, right? Here, exactly one solution. Okay. Okay. Cool. Yeah, I just put the conceptual questions. I mean, I have not put the many lengthy questions. There was, I think, no lengthy question that I put it. Just simple concepts questions I have put it, right? To see, our aim from the scholarship test is to filter out the students who knows the concept. That's all. We don't want to put it too hard, neither too easy. Just the conceptual questions we wanted to put it. The system of 5 equations and 4 unknowns and is having this solution, and then they are saying if we perform the row operation, then we are getting this particular matrix, augmented matrix, and then they're asking B plus C. Okay, if you have solved one of the weekly quiz, then this is the exact similar question from the quiz. Have you solved this particular question from the quiz, from one of the weekly quiz, which is the weekly quiz number 6? Okay, if you just solve it, maybe see, in the weekly quiz number 6, we had this particular question in this weekly quiz number 6. Okay, this weekly quiz number 6 has this particular question, and this question and the question that we have asked in the test, in the scholarship test, are exactly same. I mean, just the values are changed, right? So this is the question from weekly quiz 6. This is the exact same question, I can say, that we have asked. Okay, so if you have solved this question, then you might have solved this question. That is the question that we have taken from MIT. Yes, MIT, right? And this question that I have taken in the quiz, in the scholarship test, that I have taken from one of the, again, standard university. Okay, so see this question, even the options I have kept same. Okay, so this question we have taken in the quiz, in the scholarship test, we have taken this question from the standard university, this university. Okay, the question source, and the question that we have asked in the quiz, weekly quiz, that I have taken from MIT. Okay, so now let's just solve this question. So what they are saying, that you have ax equal to b. I mean, they are using capital B here, they are using the capital B, but that's okay. I mean, you can use small b also. I have not changed it from capital to small, but you can change it. I mean, doesn't matter. So they are saying that you are having this as a solution. Now if we perform the row operations, then you get this, right? Now first tell me, let's suppose this matrix is R. I mean, this particular matrix, let's suppose, is R. Okay, so which means what I'm trying to say is this. Let's suppose this is R. Okay, which we have got from A. I mean, we had A. Okay, we had A. Let me go to the next page. We had A. Sorry. Okay, so I'm saying that we had A, and we did some row transformation to get this R. Now, if I'm getting this R, now what we can say? We can say that whatever the solution for this this A, I mean, if Ax equal to 0 satisfy here, the same x will satisfy here also. I mean, the solution doesn't change. Then that's the only reason we are doing the elementary row operations, right? I mean, you can say row operations. I mean, the solutions, if x is satisfying here, then x will satisfy here also, right? Right? So basically, if x is satisfying here, if x is ax equal to 0, because you know the columns relation will be same. If that x is giving you 0, then this x will also give you 0. The solutions doesn't change. So they are saying that this is a solution of ax equal to b. Okay, I mean any ax equal to 0, x equal to b. So basically this is also the solution. I mean this particular matrix R into the same x must be having the same b. I mean this b, that whatever we are having here. So basically you can put this x, you can put this x, multiply with the R, and then you can compare ABCD. So one of the x, let me take one of the x, you can put s equal to 0, and then you will be getting one of the x. Okay, so by putting s equal to 0. Now see, this is the R we have into x, okay, into x should give you the b. And what is that b that we have is 1ABCD. 1ABCD. This is the crux of this particular question, 1ABCD. Okay, this is the crux of this particular question. So you can take the x, you can take any x, since it is parametric form, you can take any x. Let me just see that if s equal to 0 will work. I mean you can take s equal to 1, s equal to 0, you can take any x from here by taking, let's suppose s equal to 0, I'm getting x equal to 0 1 0 1, right? You can try putting this 0 1 0 1. If it doesn't work, I mean doesn't work, which means if it doesn't solve my purpose of b and c, I want to get b and c, let's just see. Then we may be putting some other 1 0 1 0 1, which means 0 times this, 1 times this, 1 times this vector, 0 times this vector, 1 times this vector, which means you need to add both of this. 2 minus 1, 1 plus 0, 0 minus 6, 3 minus 4, and 0 minus 11. Okay, this vector must be same as 1ABCD, because that's the solution, that must be same. See, this 1 and 1 is matching, and that must match. You can take any x from here. Okay, you put it here, you will be getting the 1 only. That is must. Okay, that is must, that you must be getting, because that's the solution. So you will be having, this is 1, this is again 1, this is minus 6, this is minus 1, this is minus 11. So b is minus 6, c is minus 1, d is minus 11, a is 1, right? So these are the answers. They are asking b plus c, that's why the answer is minus 7. Okay, so here the answer is minus 7. That was nice question. Were you able to solve that question? That was the question, exactly same as the quiz. Okay, almost same as the quiz, I can say. And that quiz question I have taken from the MIT. Okay, so now let's talk about the question number 18. That's also a bit interesting question. I mean, they are asking a square into 4 3. As you can notice, let's suppose that this is u. Okay, u is, let's suppose 1 1. As you can notice that this is the eigenvector. So with the corresponding value 3. So which means this is given to you. V is, let's suppose 2 1. So AV is given to you minus 2V, right? I mean, this is what given to you. Now this 4 3 is nothing but 2 times of 1 1 plus 2 1, right? Which means 2u plus v. And then they're asking a square into 2u plus v, where u and v are the eigenvectors. Right? So they are asking a square into 2u plus v. Let me first make a into 2u plus v. Okay, let's first solve for a into 2u plus v. So this will be, I mean, this outer a will be same. This will be a into 2u. It will be what? 2au plus av. Au you already know, since it is an eigenvector. What is the corresponding eigenvalue? Okay, 3 is corresponding eigenvalue here. Minus 2 is corresponding eigenvalue here. Okay, so basically this will be 3u. So that's why, since this is 3u, this will be 3u. This is minus 2v, right? So hence this is equal to a into 6u minus 2b, right? And which is same as 6au minus 2av. Again, this au is 3u. Again, this is 3u. So this is 3u. This is minus 2v. Minus 2v. So that's why this particular quantity 6, let me just do that way. Let me write it here. This particular quantity will be 18u plus 4v. So finally you got 18u plus 4v. Okay. So someone is saying we can use Kelly-Hamiltonian. You can use Kelly-Hamiltonian if that is preferable. Okay, not an issue. So 18u plus 4v, that's what we are getting here. So which means that 18u plus 4v, and u is this one, which means 18 times 1 plus 4 times 2 should be our answer, which is I think 18 plus 8, 26 and 22, which is B is the correct answer. Okay, cool. B is the correct answer here. Now let's just solve this. So this is question number 19. Yeah, in the question number 19, I think one of the option, maybe the option C, right? Option C. So I will check about the option C and then question number 20. So these are the only two options, two questions which are left. So I think there is some ambiguity in question C. So on option C, but don't worry about it. We will just check it. Okay. So they are saying if A is 3 cross 5 matrix with 3 pivot, then the equation Ax equal to B has at least a solution regardless of what is B. So they are saying that if we are having 3 cross 5, which means 3 rows and 5 columns, right? Then the equation Ax equal to B has at least one solution. If they are having 3 pivot, do you think this is true? If you are having 3 pivot, which means every row is having pivot, right? Every row is having pivot. If you are having 3 pivot, then it means every row is having pivot. Or another way, like you have R3 and you have got 3 columns. I mean 3 linearly independent columns in R3. Then there is always a solution, right? Okay. So basically A is true. What about B? B is saying if we are having 5 rows, okay, and 3 columns, 1, 2, 3, 4, 5, which means in vectors in R5, 3 vectors in R5, then it is not necessary that you will be having the solution. So that's why it is false. Why? Because it need not to fill the space. 3 vectors in R5 need not to fill the space. Okay. Let's just see this option C. If Ax equal to 0 has infinitely many solutions, right? If Ax equal to 0 has infinitely many solutions, then Ax equal to B has infinitely many solutions. If it means that columns are linearly dependent, but does this mean that A will be like Ax equal to B will be having infinitely many solutions? Actually, this B could be, it need not to fill the space, right? So B could be out of the space also. So that's why, there may be no solution also. So, this Ax equal to B may not be having any solution also. So that's why the C is wrong. Actually, from the university I have taken, they have made the C as correct. Maybe their context is different or the answer is wrong. But as we can see that Ax equal to B may not be even having any solution, right? Why? Because if Ax equal to 0, see, Ax equal to 0 has infinite solution. Then what does this mean? Columns of A are linearly dependent. And then I can say that Ax equal to B may not be having any solution at all, right? maybe this B is not in the column space, or this need not to fill the space. These columns need not to fill the space. How many number of columns, whatever the number of columns are there, these are the linearly dependent columns. That's what I know, linearly dependent columns, but need not to fill the space also, right? So no solution is also the case. So that's why this is wrong. I will make it correct in the sense that in the answer key I will make it correct. We will do it. Okay, don't worry. If ax equal to b has infinitely many solutions, then ax equal to 0 has infinitely many solutions. What do you think? That is true, right? If this is having infinitely many solutions, then it means that columns of A are linearly dependent, and this always have one trivial solution. Always have one trivial solution. If columns are also linearly dependent, then always have infinitely solutions. So that's why D is true. So here A and D are true. Okay. Okay. Yeah, I will make this C option false. Don't worry. Now what about this particular question? Let's just see this question. They are saying that which of the following is true are necessarily having 3 linearly independent eigenvectors. Which of the following 3 cross 3 matrices? 3 linearly independent eigenvectors you need. A matrix with distinct real eigenvalues? Yes. That's what we know, right? That's what we know. A symmetric matrix with 2 real, see, if it is a symmetric matrix, then yes, linearly independent eigenvectors. That is a property of symmetric matrix. A matrix with real eigenvalue is lambda 1, a matrix with real eigenvalue lambda 1 of algebraic multiplicity 2. So what they are saying is that you are having a matrix which is having you are having a matrix which is having lambda 1 of multiplicity 2. So if lambda 1 is having multiplicity 2, since it must be having, which means lambda 1 is repeating twice, right? Lambda 1 is repeating twice. Since it is 3 cross 3 matrix, it must be having one more lambda. Let's suppose it is lambda 2. Now this will be one linearly dependent, one eigenvector which will be different from this, because lambda 1 and lambda 2 are different, and from here we have got 2. So ultimately we have got 3, right? So that is fine. Ultimately we have got 3. Now here they are saying that lambda 1 can be repeating 2 or 3 times, which means it might be the case that lambda 1 is repeating 3 times, which means there is no room for other lambdas. Lambda 1 itself is repeating 3 times. Now lambda 1 is having just 2 eigenvectors, 2 linearly independent eigenvectors. So I don't have any case where I have, where I can have 3 linearly independent, because lambda 1 is only the eigenvalue and which is having just 2. This could be the case, right? If it is having 3 multiplicity, then in this case I will be having just 2 linearly independent, not 3 linearly independent. So that's why this is false. Okay. So A, B, C are the correct answers here. Have you understood this? Let me know if there is any confusion. Okay. So A, B, C are the correct answers here. This was a nice question, I think, right? This was a little nice question. So we try to cover in this particular scholarship test. My aim was to cover from the linear algebra. My aim was to cover the complete linear algebra, right? Complete linear algebra. We have even touched LU decomposition. We have touched symmetric matrix eigenvalues. This concept, symmetric matrix eigenvalues, these things, multiplicity and these things, right? Symmetric matrix eigenvalues. And many concepts we have touched. So complete linear algebra, I think, was covered here. Someone is asking, in the symmetric matrix, the number of eigenvectors are n or eigenvalues are n? Number of eigenvectors are n. In the symmetric matrix, number of linearly independent eigenvectors are n. Okay. So that is there already in the lectures. So in the symmetric matrix, number of linearly independent eigenvectors are n. So basically, the symmetric matrix itself is enough. With two eigenvalues, 3 eigenvalues doesn't matter, because if it is symmetric matrix, I will be having 3 linearly independent eigenvectors. That's all. Okay. The additional information is not required. Whatever additional, not required. I think these are the only questions, and the remaining questions were from 20 questions were from linear algebra, and remaining questions were from the combinatorics. Okay, so I hope you liked this session. If you liked it, if you liked the complete analysis, please do one thing. Please comment. Okay, anything. Nice session. Okay, I can give you the suggestions. Just comment nice session. Understood everything. Or let me know that the quality of the questions. Quality of the questions in comment. Okay. So I hope you like this test. You like the analysis also. Okay. So just comment it out. Okay. Please don't forget to comment. Please comment. That's the humble request. Okay. Please comment. Okay. So thank you everyone. If there is anything else, you can just ask us on the Telegram. Just don't forget to comment. Okay. Just comment anything, whatever you like to comment.